Hi there, I'm Randal Sagrillo with the Systems Group here at Oracle. I'm here to talk about how you can be a hero with your DBA. Basically, we're going to talk about how to tune systems to make databases run better. I've actually been doing this kind of work for quite a while. Even though I'm doing mostly solution work today, really done a lot of work as actually a performance engineer. And for those of you who don't know, you may think performance engineers are guys that like to make stuff go really, really fast. But really what I like to do is get systems to saturate at the same point. And what I mean by that is all the bottlenecks in the system, I want those to hit at the same point at the same time for the most different types of workloads as possible. In doing that, we end up reducing the cost of the deployment in addition to getting that great performance. The way I'll talk about it today is to kind of give you some background on the methods that we use to analyze systems, some of the tools that are used in these cases. Many of you who may actually be DBAs are very familiar with these, but those of you who do platform tuning or systems tuning may not be familiar with these tools. Then the meat of it, the examples, and how we actually look at what I believe to be one of the best instrumented pieces of software on the planet, the Oracle database. And then where you can get more information if you want to go further. Bluntly, we're going to spend probably less than an hour talking about it in this session. I could spend days talking about it. This is actually a very broad and rich topic, so I'm going to just focus on those situations that are related to online transaction processing, some mention of data warehousing, and again, we're just going to pick the top 2 or 3 major issues that customers see in real-world deployments that you could really be a hero with tuning a database platform to run a database better. The other big caveat I do need to give you is, bluntly, I do get involved in tuning the database from the software perspective, looking at the SQL and the instance, but I'm not going to have time to do that today. So we're going to make a bad assumption, which I hope you'll bear with me, that somehow magically all of that other stuff is perfectly tuned already. That's not a good assumption in the real world, but to make today's session more interesting, we're going to assume that somehow magically that's already happened as we're doing our analysis in our examples. So ultimately, my only close thing to a marketing slide here, by the way. I do want to let you know that we do understand that there are a lot of pressures that go on with deploying systems today and deploying databases and enterprise applications. Overall, over time, there's more of everything, more users, more data, there's more transactions, and a lot more complexity in the overall business processes. And ultimately, this means that you don't have as much visibility. We want to get to a more real-time view of visibility. Usually the batch times and the transaction times get longer as we put more users and have to look through more data, ultimately lower performance, and overall less agility with how we run our businesses. So what we're really trying to get to here, and this is just one part of the equation, is we really want to get to the real-time enterprise where it's kind of cloud everywhere, in-memory everything, and even some of the things like software and silicon. This is really where we're going. But you're not going to require any of that to what we're going to do today. This is a starting point so that you can be better set up to accept these kinds of technologies. So just a reminder where we're going to look at. I end up hearing issues with what's going on with a system from a performance perspective. And most people talk about, wow, how many transactions per hour I can do, or how many millions of TPMC, or things like that. That's talked about, and that tends to be more of a marketing issue. Most of the real world issues that I end up dealing with are related to a batch time is too long. I've been recently working with financial services customers, and every day they're going through water torture. They're trying to get a batch done before the next day's business begins. I've been in several large services businesses that ultimately every month they're trying to close, and they can't get it done over the weekend, or maybe even can't get it done over a reporting period. So often things like these batch jobs end up being one of the biggest indications that your reach has exceeded your grasp in terms of how the system is put together. And you've done all the things that you've already can do from a software perspective to make the database run faster. You've really tuned the SQL to the best of its ability. The other one that we end up seeing is a lot of reporting issues. We're doing more ad hoc queries and trying to do more real-time decision making about our business. And then the last one that I see of the top three over and above this rate issue is that actual transactions take too long. And for some businesses, these transactions times, they don't measure them in milliseconds. They'll laugh at you. They want to measure in microseconds because these are usually things like trading or arbitrage. So some of the things that we're going to talk about today actually apply to all of these, but we're going to focus typically on the top 2 or 3 here in terms of what we can talk about in this short discussion about how to be a hero with your database administrator. Okay, so stepping back, I always like to say it's all about I/O. Myself as a performance engineer, and when I put on that hat, I'm trying to balance the system. I'm trying to balance CPU, network, storage, really all the different kinds of I/O and memory. And kind of one of the big things that you're going to end up seeing here is there's all kinds of different I/O profiles. Most of us think of network I/O and disk I/O, you know, the physical I/O. But one of the big statistics that's maintained within the Oracle database is something called logical I/O. This is basically doing an I/O to something that's actually in memory. It's actually in the buffer cache. So maybe we're talking about, in our example here, a database that's, say, 4 terabytes. And the 4 terabyte database, I may not be working for my workload with all 4 terabytes. Maybe I'm only working with 1 terabyte of it. So maybe I only have a 1 terabyte working set size. If I'm really fortunate, I've got a really big system, maybe I end up having 1.5 to 2 terabytes of physical memory, and a lot of that I can give to the system global area. And in that case, that means that all the queries and all the DML are going to operate on memory, and so all the I/O is logical I/O. So there's not a lot of physical I/O. It's like a small portion, maybe 20%, 10% less. So if you're fortunate enough that your 80% of your SQL processing time is actually for the database as CPU, you've got a pretty well-tuned system in terms of the balancing. But you probably maybe need more CPU, but we'll talk about what that is. In this case, faster CPUs usually mean faster memory and more memory. So what I'm trying to say is, if you've ended up going from an old system to a new one, you might think that actually it's the clock speed of the microprocessors, but often what is happening in the real world when I've analyzed them is the fact that modern processors have more memory channels and a lot more memory. So ultimately, what's ended up making something that says, like, I didn't change my storage, I put my new system in place, and I put these brand new CPUs that are just really fast, but when you really carefully look at it, what's really going on is you typically have a lot more physical memory, and that ends up doing less physical I/O, and the database can perform faster. So even though this is really about CPUs, there's a lot going on here with I/O, this logical I/O concept. On the other side is what I end up seeing in the real world a lot, not in the benchmarks, but in the real world, and it's physical I/O, and we're going to talk a fair bit about that and how we mitigate that. So I have the same database here, right? You know, maybe I have a 4 terabyte database, 4 terabytes of relational data, and now maybe my working set size is bigger. Maybe it's closer to half the database size. Maybe it's, you know, closer to 2 terabytes. Maybe I'm not so fortunate. I've got a smaller amount of physical memory. So now my working set size is much bigger than my physical memory size. That means the database is going to have to go and get the data from the storage subsystem and put it into memory so it can operate on it. You know, microprocessors can't actually operate directly on the data in the storage unless you have something cool like an Exadata or an Oracle supercluster. So in this case, this ability to be able to operate on and minimize the I/O and the wait times can help. The big message here is, if you're, and we'll talk about how to look at this, if you are on a physically I/O bound database, faster CPUs aren't probably going to help you that much because you're not spending that much time on the CPU running your system. So a little background here on this storage, just so we're on the same language. everybody loves to talk about IOPS. I mean, as I said, as a performance engineer, IOPS are a big piece. And it is very important for sizing, but it is not the key metric that we're going to use to figure out how to make our enterprise applications run faster. So, you know, if I was, say, Facebook, maximum IOPS deliver is a measure of concurrency, and I might need lots and lots and lots of concurrency because I've got millions of people, hundreds of thousands of people concurrently accessing a system. So talking about those IOs and that IOs per second, if it's 1 million IOPS or 100,000 IOPS or 3,000 IOPS, that's really a measure of concurrency. And it is important for sizing because it basically is related to the number of concurrent streams or the number of users. But having more IOP capacity available on the target does not necessarily correlate to getting more performance for your application. So the next one, which I like to call the Exadata metric, is really my data rate delivered. How quickly can I read, you know, how quickly can I do direct path inserts, and mostly direct path reads. I want to be able to search, you know, do those needle and haystack searches for the critical data that's in my database. And so it often is limited in standard deployments in things where you don't have the value of engineered systems like Oracle Supercluster or the Exadata database machine, how many gigabytes per second you can scan in your storage system. So that is talked about less, is that gigabyte per second, or that maybe if you're not so fortunate, the megabytes per second at which you can scan. But even that is not the big one, particularly in the OLTP workload. For both OLTP and in many data warehouse workloads, what you find, it is the service time. How many milliseconds or microseconds does it take for a particular operation? Every microsecond you can shave off ends up being time that the application is not waiting. So obviously if you don't have enough IOPS capacity or enough data rate capacity, you will add queuing time to the service time, the response time of your storage subsystem. But what we're going to be looking at now, as you're going to see when we look at the instrumentation within the Oracle database, we're going to look a lot at these response times or service times for these off CPU wait events. So step back on the methods that we're going to use. It's pretty simple. First, start with the symptoms. If we're having a problem, tell us what the problem is. Is it in the middle of the day that my response times are getting sluggish for all my users, and how many users do I have? Or is it that batch job that's running between 3 and 6 in the morning and I need it to really finish by 4 in the morning? Or whatever that particular metric is. You want to understand and identify what the service levels are and the conditions that they're under. Then you want to go ahead and diagnose this. I cannot emphasize enough that when people are doing these kinds of analysis and performance tuning, you got to clearly identify the SLAs and narrow down the window that you're analyzing to the area where you're having the problem. If you're having a problem an hour every midday, as I talked about before, where say between 11 and 12, the response times are really horrible, that's the service level, and you analyze data for the entire week, you may not be able to find what's going on. You need to look at those shorter pieces of data where you're actually having the problem and correlate what the SLAs are and what the workload is, and we're going to show you how to do that. So again, take that narrow data, that's really the biggest advice I can give you, and then go into your diagnosis and analyze, and then of course apply the tuning tips, and then go back and keep doing this till you get where you want to get, meeting your service levels. So some of the tools, again, I mentioned that I've done a lot of performance engineering in my day. I love looking inside the operating system. This is normally one of the great places, and Oracle has some great technology. We have something called dtrace, if you've heard that, in Solaris. We're looking at moving that elsewhere. That is a really cool tool, tells how the applications see the operating environment. We've got some great tools for doing workload analysis at the storage level. These are very powerful tools, but they don't, what they do, they're really seeing what the operating system is seeing. What you want to see is what the database is seeing. So what we want to do is move into utilities that look at how does the database see its operating environment. So many of you that will do SQL tuning or try to do instance tuning of a particular database have used things like SQL tracing, SQL tracing, TK-prof. There is a free utility out there, Statspack, that was supported, available since Oracle 8i, and that's a good one. We'll talk a little bit about that. My very favorite is the Application Workload Repository, or the AWR report. I think this comes with some of the best money you'll spend with Oracle, and that's the Oracle Diagnostic Pack. So there's a number of tools within the Diagnostic Pack. There's also the Oracle Tuning Pack, and this again focuses more on how you're going to tune the SQL software. But here we're going to understand how to make the platform better. Remember, we're trying to be a hero with the DBAs. We're assuming that they've already done all the SQL tuning that they can do. How can we tune the platform and use the Diagnostic Pack? And my view is use the AWR report. If you're not in a position or unfortunately don't have access to the Diagnostic Pack, for extra work on your end, you can manage, install Statspack if you've got a service agreement with Oracle. That's downloadable PL code. But again, you have to manage it and do all the work. The nice thing about the Diagnostic Pack is that it does a lot of that work for you. So it makes your life easier. Okay, so I said AWR and Statspack report. They report the same thing. This is actually an example from an application workload repository or AWR report. And I will tell you, this is one of the first things I look at. Why is that? Remember what I said before. When's the problem happening and how long? Here's an example where I've got 60 minutes of elapsed time that I'm looking at. So where I'm trying to characterize the performance and what's going on in the system and what the workload is when I'm having this problem, or this level of service level not being met, takes 60 minutes. Notice that the database itself is multi-threaded and sits on a modern multi-core, multi-threaded system, so it can actually spend more time running than the real time. You and I look at the clock and see an hour went by, but the database is running multi-threaded over many cores, and maybe it's spending several hundreds of minutes, maybe 5-6 times longer. I've seen much higher ratios than that. So that's usually the first thing that I look at, is right at the top of the Statspack report or the top of the AWR report. And this gives me a lot of information, what the platform is, how many CPUs, how much physical memory is allocated to the system running the database, whether I'm running rack, what the version of the database, all that important stuff that you want to make sure that you're talking about the same thing so you know where to go look for that particular version of the database to analyze your issue. But the first thing I always look at is how much elapsed time. If someone's saying I got a problem for an hour and this snapshot of the workload is for a week, I'm probably not going to be able to find it, and I got to give that customer or prospect the bad news that I need a narrower snapshot to get the data, and you will too. So remember what we talked about before in terms of balance. Here is a particular snapshot from a real live customer system. And notice that this first thing, what is that? DB file sequential read. If you've been around databases a long time, that is, as you know, the poster child of wait events. And notice that's an off CPU wait event. It is not executing on CPU. So we're spending, in this case, we're spending almost 2/3 of our time, 58% of our time, waiting for user I/O to complete. We're going to talk more about this. But notice what the second wait item, the second most predominant time over this snapshot, in this case we said an hour, is database CPU time. And we're only spending 16% of our time waiting for the database CPU to complete. So let's think about this. If I made the CPUs a lot faster, or added potentially more of those CPUs, remember I'm not going to pretend I'm changing memory, I'm not going to change the I/O profile, would this run faster here? The answer will generally be no. You're not CPU bound, you're really I/O bound. And as you can see, the wait class that's defined in these top 5 time foreground events is user I/O. So that's what you really want to focus on. And this is, again, very common in the real world. You know, if you've gone this far in this discussion and all of your AWR Statspack are all CPU bound, a lot of what I'm going to talk about probably won't help you. You have to do other things. Maybe I need to focus on getting more CPU power. But in the real world, this is a lot less common than you might think. When we do benchmarks, we're very good about tuning everything out so we can get the maximum out of the database CPU. But in the real world, there are usually network waits. We're waiting for the application in some cases. But here, we're going to focus on those wait events that are associated with the platform. That is, the networking, the operating system, the servers, the virtualization, and the storage. We're going to look at what's happening there. So, you know, I'm going to say something later. Google is your friend. When I started doing this kind of work, I had to look up these wait events and what they meant. Here is a short summary of some of the key wait events. There are, and for those of you who are familiar with how the Oracle database works, there are foreground processes, those that are kind of facing the application or facing the customer, as you will. And those foreground events happen on session processes. So when one particular piece of SQL is being executed, for example, let's go select to go find something. If I go and do that select and the data is not in memory, that session process on most any platform will simply go to sleep. Nothing more is going to happen on that session process. So we're going to have to wait for the data to be brought in by the disk, brought into the system before we wake up that session process. And that's why this is such a common. So this is called a foreground wait event. It happens right in foreground, right where these server session processes are interacting with your enterprise application, whatever that application may be. And by the way, that's the #1 event here because that's the #1 we tend to see in the real world. And if you're like me, you've probably seen the same thing. The #2 we'll talk about, and we'll spend some time in this session, is log file sync. And so this actually is waiting for something to happen in the database background process. But it is actually referenced from a foreground perspective, from the application's perspective. And we'll talk more about this later. There are a number of other foreground wait events. I'll just quickly cover them. There's many, many more than this. And again, Google is your friend. You can look these up. They'll explain what they mean. And often there'll be some very good advice out there as to what kinds of tuning tips or changes you can make to your system to make it run better. But we'll focus today on DB file sequential read, you know, that foreground disk block wait, and then the log file sync, taking for the application to commit all of the stuff associated with a particular transaction. Just a quick, again, couple quick things. So scatter reads, those are typically multi-block reads going into different places in the buffer cache from usually a single physical read. I mentioned read by other session. If you're a very heavily hit online transaction processing database, whatever that application is, what you'll find is other sessions are trying to get to the same block. So the Oracle database is very smart. Whoever asked for it first will get that DB file sequential read, and then another session will get that read by other session. And once the first session is serviced, the second one will be woken up so it can go and deal with the data modified or not. And the last one I'll mention, which is not a buffer cache issue, are these direct path reads. I mentioned those a bit before. I call those the Exadata wait event because Exadata does such a great job managing these. With direct path read, we have to go scan through the data. We're doing typically some kind of projection or filtration, looking for some particular data in some large full table scans. And those end up being direct path read type wait events. So if you've got those, we probably won't talk about that. You may probably want to look at something like Exadata or really tuning your large full table scan type queries and minimizing those. Couple quick things on background events. When I'm actually writing the redo log, you know, this is very important for the commit process. That's that log file parallel write, and that's usually one of the top wait events in a busy OLTP database. Interestingly, and it's very service time sensitive, and we'll see that. So the time it takes to do that write in background obviously will have a big effect on how long it takes for the application to get synchronized and realize that the write is complete, so it can say the commit is done to the application so the application can move on. One that is not very latency sensitive, so this is one you don't have to worry about, but I mention it, is something called DB file parallel write. The Oracle database often will have many writers to write the data asynchronously in background. So once a particular transaction is committed, there's been some change, some DML, those data blocks can be written 50 milliseconds later, and that often, not always, will not really have any effect because the application moved on when the commit completed. So I apologize for this kind of database 101, but I want to mention it because you're going to have to look at it from this perspective to be able to analyze these kinds of problems. And then, again, Google is your friend, log files, sequential reads, log archive IO, RMAN waits. You'll see all these kinds of things in the background. You can determine whether these are impacting your system or not, as we'll talk about in the rest of this session. And if it's one that I don't have here, look it up. There'll be lots of great ideas by many others out there, and maybe someday you'll end up posting about how you dealt with one of these and became a hero with your DBA. So let's go to the first example here. This is actually kind of a lab example I like to share. In this particular case, we have this is a insanely, it is something that we're trying to understand the behavior system, but a very high commit rate online transaction processing workload. And if you're doing a really high commit rate, you would expect that you're spending a lot of your time, as I said, waiting for log file sync. And as you can look at this report, we're spending almost 40% of our time waiting for commits to complete. That's a lot of time. That's not, again, really CPU. I'm not executing CPU. I'm just waiting for things to happen in the system, usually in the write aspect, in that background writes, to complete so that those sessions can move forward. The next one is this poster child event, this DB file sequential read. And you can see over this snapshot. Now, I'm going to tell you how big this is. You're going to think I'm crazy. These are about a 10-minute snapshot here. So we had, this is, again, we're doing some testing in our lab to see the limits of a system. I wouldn't expect this in the real world, but we've got, 500 million events going on. Again, a lot of them are concurrently. And we're running with really, really fast storage. We're trying to find the limits of the system. So in this case, this is about 3/4 of a millisecond is the average wait time for a block. That's, you won't see that in most customer environments because we're just trying to find out how fast the rest of the system is. But how could we tune that and make that better? And so again, this is a flash-based or a really high-speed solid-state disk-based storage solution. We want to reduce that DB file sequential rate because we know the log file syncs are really part of my commit rate, and I'm probably not going to be able to deal with those in first order. So how do we get more CPU time to get more work done so we're not waiting on these off CPU wait events? Well, one of the things that you'll do is look at something called the buffer pool advisory. So again, at the very top is that, how much time, how long is the snapshot, and right down below that is all this good stuff about what the top wait events are. But deeper in the report, you'll find something called buffer pool advisory. And this is going to tell you about, help you make estimates as if I was to increase the size of that memory, how much fewer physical IOs would I have to do? So and if you're more sophisticated, you can look this up. You may want to split your pools differently so that you can be more efficient about looking through them. And then, of course, we can isolate these really busy tables. Those tend to be more on the software side and instance tuning. But the big thing on the system is, can I find a way to get more memory to this database process? One thing that if you can't do that, the next best is to use something called flash cache. So what I'll do is, in this case, we have all of our relational data in flash, so it may not help as much, but if I don't have enough room in memory, I'll go to flash storage and keep cached copies of the memory data in some really fast storage, so I can kind of deal with it as a level 2 cache. So it's kind of a second order buffer cache. And this is something that's used in a different form in Exadata and Oracle Supercluster, in something called Exadata Smart Flash Cache, and which you probably have heard of, I assume already. So that's one way. And of course, Oracle Database has something called Oracle Database smart flash cache. So a little different technology, but they work the same way to make those reads faster if I don't have enough physical memory to do the reads out of. So this is an example of some things that we did in our lab, and notice what happens as I reduce the number of physical IOs per transaction. And one way to do this is to give the system more memory, or to potentially optimize your SQL, your SQL. So in this case, just making the changes that we were able to do in this particular case, going from 8.5 IOs per transaction to 1, we got a big jump, 1.6x throughput. Now, most of it comes in getting at that last point, going from 2 IOs per transaction down to 1. And that's what I typically see in the world. Normally, you're not going to have those high ratios if you've well-tuned your SQL, which again was one of my assumptions, but did want to show you just how much faster things get when you can do them out of memory. And here is actually what we saw after doing this. So if we can drop it down, instead of having those big, huge numbers, we have a much smaller number. It's almost 1/10. It's 1/8 and a half, right? DB file sequential reads. So the number of them over this 10-minute or so snapshot, the total time is a lot less, and therefore I have more time to run CPU, and therefore I can actually do more transactions and get more throughput. So that's what you actually see happening here, is making these kinds of changes, being able to move the memory around. That's one of the biggest things you can do. Or pick platforms. If you're purchasing a new platform, I want you to strongly encourage to, fast CPUs are important, but make sure that you've got more memory. Having more memory, if your database profile is IO bound, which I see so often, that's one of the biggest things that can help. And how much we'll talk about a little bit later. Okay. So here's actually something from a customer site. So again, DB file sequential read, poster child. This particular situation, we wanted to reduce the IO burden on a really large storage system. So, if we're going out to the storage system, that costs money too. So maybe I'm not trying so much to make my system run faster, but I'm trying not to have to spend millions and millions of dollars putting more storage so that I get those shorter response times. And remember, as I said earlier, performance engineers are more about balancing the system, making sure everything saturates at the same point. That's typically how we reduce the cost, and we all know how important it is to reduce the cost so that we get the best total cost of ownership. All of this knowledge comes from co-engineering, engineering between people that understand the database software and understand the platform. So that's really what we're trying to get to. And in this particular case, this was a Spark T-Series system running Oracle Solaris, and it actually was running a real application cluster in this particular situation. So here was the profile we have, and these are 15-minute snapshots. And just some of the things I want to point out to you here when you look at this. Here's a 15-minute snapshot. Notice I've got hours. I've got like 9 to 10 hours of I/O wait time in 15 minutes of real time. So again, it's lots of concurrent sessions are all asleep, nothing happening. The application can't move as fast. So I'm only spending 20% of my time, 22.4, waiting for CPU. Most of my time, I'm waiting for IOs to complete. And look at the times here. It says the average wait is about 11 milliseconds. And for those of you who know storage systems, that's a pretty good time. That's not bad. It's not great, but it's not like 100 milliseconds. So on average 11, and it's really slowing us down. And I'll mention in that same 15 minutes, we have also lots of concurrent commit time. There's 77 minutes of concurrent time. And the way I compute all these is I go look at that third column, that time in seconds, and I just figure how much minutes over the snapshot I'm spending doing these activities. And when I understand the off CPU wait events, that I can typically do things to tune the platform, be it network virtualization, how much memory I'm assigning between partitions, or maybe I just need to tune up my IO stack. So what we did in this case is, I would typically go to an Exadata or an Oracle supercluster, but in this case, that means buying and spending money. In this case, we did something much smaller. We did a database smart flash cache. So the beauty of this is, just so you know, even though this looks like storage, it's not, because if the storage fails, all I have to do is go back and get the data instead of from this flash cache back from the disk system. So I always have my good data. So this is what we'd call a clean cache. There's never dirty blocks that don't sit on storage. The blocks that sit in the flash cache are clean, and we typically want to make it a lot bigger than the system global area size because we want to offload the buffer cache, the bottleneck that's occurring there. And as you would expect, this is typically for read workloads, although taking I/O workload off the storage subsystem, because I don't have to do so many reads because I got the flash cache, can make writes go faster too. So this was after that same system, after we optimized. Notice what happens here. I'm now spending almost 2/3 of my time doing CPU. The customer got what they wanted. We had a huge reduction in the number of reads that were occurring on the storage subsystem, but I'm actually getting more transactions for every database node, and that made the customer very happy too. So this is a pretty typical class of problem that we can go after. I'm going to give one more because all these things I've been talking about, millions of transactions. What if something is a little bit smaller? So this was actually the one that I started my example, my 1 hour snapshot. And here I was trying to understand what's going on in a financial application. I wanted to do some bank processing in this particular case. And I have a very tiny buffer cache, only 2 GB, because this particular database, as you can see, only has 14 GB of memory. And you can see that there in the second row where we have the host name and the platform and the number of CPUs and the sockets and all that stuff. You see we have 14 gig. 2 of that's for the buffer cache. So in a 1 hour snapshot, we're doing 1 million waits in an hour. But if you go and figure that out, an hour has 3,600 seconds in it. That's only 200-300 IOs per second for foreground just for these reads. That's not a screaming rate. And my laptop can do IOs that fast. So this is a very important system for a customer, but the fact that it's not a lot of IOPS, it's not about the IOPS, it's about that 10 millisecond wait. If we can get that down. So if I had more memory, I would give 90 gig of RAM, but we didn't have that opportunity in this case. We wanted to show that, in fact, it wasn't really about the CPU, because you can see here, I'm only spending 16% of my time on the CPU. We have to balance the system. We have to make that time longer, and if you can't do it through tuning your SQL, you've got to look at your platform. So in this case, instead of adding memory, because I couldn't, because this is a little bit older system, we added some flash just to see what would happen in this particular case. And what we saw here is that now the average time, instead of being 10 milliseconds, ended up being, we look at the IO wait time and the number of waits, it ends up being about 1/2 of a millisecond. So it's about 20 times faster. And in the end, that meant that the application response time was cut in half. And so and ultimately, when you really analyze this, I was doing fewer index reads out of storage. I was end up doing them out of a cache, ideally a buffer cache if I can give it more memory, and if not, a flash cache, or if I'm fortunate enough, something like an Exadata or a supercluster. Now, and this is a little hard to read, but I want you to look at it. So my going away point here on DB file sequential read is, how do I know how much it's going to help? So take a look at this one, and if you look on the left-hand side, you see a amount of buffer pool memory, and you see there's a factor there. And when you're at 1.0, that's basically the size of the system as it was instrumented. And we can start making assumptions. What if I was to steal memory from the buffer cache in the SJ and give it to something else, maybe make a bigger PGA? And you can see what happens to the physical read rate. How's that going to affect transactions? And go the other way. Let's add memory. This is the database estimating over that workload. As I add memory, how much fewer physical IOs? Well, take a look at this one. If you look at the estimated physical reads, you're going to find that doesn't change. So the sad truth is, in this case, adding more buffer cache through flash cache or using your virtualization technology to move the memory around, the database is telling you it isn't going to help you very much. What this means is that you've got very wide skew. You have a very large relational database, and you're grabbing data over a big piece of it to fit into a small amount of physical memory. So you'd almost have to you'd have to go to in-memory, right? Move the whole database to in-memory, and if you can afford that, great, and that's how you can make things faster. This is much more typical. This is a modest increase, and here you see looking at the same data, if I double the size, see that factor there, that size factor, if size factor goes from 1.00 to about 2, you see that there's about a 12% drop in the physical read rate, and again, that's time that's going to be available for CPU processing, which is going to make the system run faster. And in some of the examples I had for those advisors are much more marked, or maybe we just need to add a lot more memory, something like a flash cache, or you're just going to have to go to an engineered system like a Oracle supercluster or an Oracle Exadata, depending upon what this profile tells you. So I'm just giving you a little hint here how to look at the buffer pool advisory and see, is this really going to help my DB file sequential read by having more memory or not? So, in summary on this big tuning event, 2/3 of these databases, this is usually the majority weight of it, what I see in the real world. And by the way, we always talk about data warehouses, you know, how fast can I scan that data? And in this case, data warehouses also have DB file sequential read, and you may have seen that in your case. So use that buffer pool advisory, try to add memory, particularly if you think it's going to help. If not, you can go to a flash storage subsystem from a vendor. I actually think Oracle has done a very good job with the Exadata storage cells with Smart Flash Read, and as we'll talk about, Smart Flash Log and Smart Flash Write for both Oracle Supercluster and Oracle Exadata. It's all that co-engineering allows us to design systems that never hit this bottleneck from the get-go. And if you're able to do these kinds of tuning and get that DB file sequential read, so it's a much smaller part, get more of your database processing on CPU, a 2x improvement is not unheard of, and it's actually happened quite a bit, and I've seen numbers much bigger than that. So, okay, we're going to change topics now. Even though this one, the #1 event here in this particular case, this is batch processing on a large, huge ERP system. And when I saw this, I thought they didn't give me very good data because this is an 8-hour snapshot, really long snapshot. And I said, gee, that's too long. When are you really having a problem? Oh, I'm having my problem over 8 hours. This is an 8-hour batch job. That's too long, right? It's taking all night. And we see my favorite problem, DB file sequential read, 5 milliseconds. That's a pretty good time for a big storage system. This is a really, really large system. But notice the next one. This is where we should be nervous. Log file sync. As I'm running this batch process and I'm committing steps in the batch, I don't do that many steps. It's like, 1/50th of the number of physical reads. But look how long the waits are. The waits are 1/3 of a second. This thing should much more reflect the time of the storage wait, which should usually be just a handful of milliseconds, not 1/3 of a second. So there's something wrong here that we need to look at. So what I notice here is in 473 minutes of snapshot, I've got 290 minutes of logging time. And how do I know that? I'm lucky enough that the log file sync, I can see the actual write going on also here in that log file parallel write. And see that log file parallel write there, it's only taking 22 milliseconds to actually write the data out, but it's taking 1/3 of a second before the application knows about it. So that's a pretty big hint. Obviously, if I can make that log file parallel write shorter, because 22 milliseconds isn't great. If I should be closer to that 5 milliseconds or 4 milliseconds or 3 milliseconds, that would help. But the fact that those log file syncs is a big problem. So as you can see, huge amounts of commit time here. How do we make that log file sync go away? This is kind of the next big problem. So again, the logging time is slow. It's about the order of 25 milliseconds, about 22 milliseconds. The log writing is only 3% of the commit time. So what's happening here? Well, let's remember, databases, most databases are configured so that they have one log writer process. So if I've parallelized a batch job and I've got lots of streams going in, they're all contending. By the way, same thing happens with OLTP workloads. They're all contending for the same log writer process. So I want to make sure that I can run whenever that log writer is done. I want to wake up those sessions as quickly as possible. And more importantly, I don't want those foreground sessions to steal the time from this important background. So in this case, what we did is we said, let's go ahead and take this log writer process, because there's only one of them, let's go find it and give it more priority. So we didn't have to change it. The tuning of the system was really to create in this case, a processor set and bind it to the log writer process. This was an older system. As you'll see here, we've put technologies in to do this more automatically with our co-engineering here at Oracle. But in your case, ensuring that the log writer process gets high enough priority, if that's the bottleneck, can really, really help. And that really improved our commit time significantly here. So, and obviously that 22 milliseconds or so, 25 millisecond write times are not great. We followed on to try to improve those later. So what can I say about log file sync and log file parallel write? About 20% of your OLTP databases will have this as a problem. This is a very, very common in batch environments too. I've seen this quite a bit. So improving the log write time will help, because that means that you're spending less time in that background process doing the write, because it's serial. It's a serial process. So if I'm doing a write, there's nothing else. All I can do is queue up more work. So making that shorter will help, but making sure that that process can run whenever it can to get those writes out is very important too. And one of the things that we have added within Oracle systems, we've added something called critical threads. This is specifically in Solaris, and this ensures that the modern versions of the database, like for example 11.2.04 and beyond, just automatically bind the log writer process to a critical thread so that they are given very high priority within the operating systems. You can do it manually, and even with older versions, 11.2.03 and 11.2.02, you can apply patches to do this. But this is something that applies to any system, no matter whether it be on AIX or Linux or Windows or whatever the platform. Making sure that that log writer process can run is an important thing. So once you're tuning the system, getting separate log devices, using something like an Exadata or an Oracle supercluster again that's got smart flash log, that magically just makes dramatic improvements in this. But you have the ability to make some of this improvement yourself, and again, be a hero with your DBA. So how can we find out more? Other examples, because again, there are dozens of wait events, hundreds of them that are tracked by the Oracle database. I'll continue to say Google is your friend. Whenever I see one that I'm not familiar with, I go search it. If you just want to learn more about the database performance concepts, you can read this. A lot of these examples were for an 11G R2 database in this particular case. So you can go look at the tuning guides, learn more about the diagnostic pack. Another thing you can do is Oracle does a lot of work to tune the database on its platforms, and many of those tuning hints and wisdom apply to other platforms. Obviously, you'll be able to apply them more quickly if you apply them directly to Oracle systems. So check out Oracle Optimized Solutions. There's an Oracle Optimized solution for Oracle Database. Give you webcasts, videos. There's online training available, usually white papers. And if not, talk to your Oracle representative. They can give you access to slides, presentations, tuning guides, implementation guides that show you how to do a lot of this stuff so that the system, once you've implemented it, will deal with a lot of these situations and many more. Hey, thank you very much for your time today.